So in this video, I want to continue talking about the runtime complexity of merge sort. And what we figured out is that this call to merge is going to take k times the length of L time. So for some constant k. That's not including the time that it takes to actually compute merge sort of L from the beginning and up to mid. And to compute this thing, that's just the call to merge. So with that said, let's try to draw the call tree for merge sort. So we'll start at the bottom, and what we're doing is we're going to be calling merge sort with some kind of list that's going to be of length n. So I'm going to denote it like that. So it's going to be a list that's of length n. That's how I'm writing it down. So this call to merge sort, what's going to happen now, it's going to get to this line and it's going to say, okay, I got to compute this thing and I got to compute this thing. So that means that this call to merge sort is going to produce two calls that would try to sort two lists of length n over 2. So it's going to look kind of like that. And then each one of those calls is also going to produce two calls to sort lists of length 1/4 n. Here you'll also, for example, have a call to sort the last quarter of the list. And that's going to go on until the point where you start calling merge sort on lists of length 1, because that's our end condition. Alright, so now in order to figure out the runtime of merge sort, you cannot simply count the number of calls to merge sort. That's because each call to merge sort actually will take, in this instance, different amounts of time. Why is that? Well, it's because inside each call to merge sort, you have this call to merge, which takes time proportional to k times the length of L in terms of operations, or in terms of seconds, whatever, it's going to be different case. Alright, so how do we now compute the runtime? Well, here's the idea. What we'll do is we'll compute the time that it takes to call merge for each level in our call tree. So for the first level, it's extremely easy. We just have the one call on the one list of length n, so the runtime is going to be k times the length of L, so kn. For this level, it's going to be kn over 2 plus kn over 2, so kn as well. For this level, it's also going to be kn. In fact, it's going to be kn for every level. The reason it's going to be kn for every level is because this is going to sum up to n, because here we have the first half of the list and here we have the second half of the list. Here we have the first quarter, here would be the second quarter, third quarter, fourth quarter, and so on. Here we have eighths of the list, and so on. So on every level, in total, k times this plus k times this is going to be kn, k times this plus k times this, k times this, k times this, that's going to be n, k times this, and so on, that's also going to be kn. Because on every level, we have the entire list. It's just broken up into halves or quarters or eighths or sixteenths and so on. So on every level, it's going to be kn. How many levels do we have? Well, that's pretty easy to figure out. What we need to do is we need to say, okay, so here we start with a list that's of length n, and here the list is of length n over 2, here the list is of length n over 4, and so on, up until the point where the list gets to be of length 1. So that means we are dividing the length by 2 every time, and we're going from n and down to 1. Now, n is 2 to the log 2n. That's the same thing. And then this is 2 to the 0. And this is going to be 2 to the log 2n minus 1. That's this number. This is n, and this is going to be n over 2, and so on. So in order to get from 0 and up to log 2n, how many levels do you need? You need log 2n plus 1 levels. So if you have log 2n plus 1 levels, and on each level you perform kn operations, then in total what you will have is kn times log 2n plus 1 operations. This works out to O of n log n, because you can ignore the constants.